Hey, Mr. J here. Gonna do some grade 4 probability. We're looking at a couple things. We're looking at coin flips and we're looking at drawing marbles from a bag. I don't have very many marbles here. Some say I've lost them. Yeah. But anyway, what I'm gonna do instead is I've got these Lego pieces and I'm gonna put them in a little jar. And I promise I'll close my eyes. So let's start with, get all this out of here. Let's start with the coin flip because it's like the easiest sort of one to keep track of probability on, because I mean, well, think about it. You know why? There's only two choices, right? I've got heads, I got the lovely queen there, and I've got tails, which doesn't actually show the tail, but trust me, it's got one. All right, so heads versus tails. So the reason why this makes such an easy probability experiment is you've only got two options, right? Whereas with, let's say, if I use dice, then I'm going to have 6 options, right? So it's a great one to start with. So in grade 4, you have kind of two jobs. One is to do an experiment and to sort of propose an experiment and propose what you think is going to happen in the experiment, and then do it. And then you actually do it and see how your results compare. So for example, with a coin, if I said I'm going to flip this coin, what do you expect to happen? Do I expect to get heads or tails? Which one do I expect more? Which one do I expect less? Whatever, okay? So my experiment is going to be flip the coin. So flip the coin. I mean, there's not a whole lot else you can do. And I think it will always be heads. That is my prediction. Think it's a good one? Let's find out. So that's my suggestion. Or maybe I'll say this. I think I'm going to flip the coin 10 times. And it will always be heads. Here we go. I don't know if I can do this while looking at the video. Oh, I can't. Well, let's count that one. Hey! Tails. Okay, so now I need some way to keep track. So there's, lots of ways. Since I'm doing it 10 times, I think sort of the easiest way is the old T-chart, baby. So I'm going to go flip number, and let's say outcome. I could have wrote heads or tails, whatever. So flip 1, 2, 3, 4, 5. Let's make this 5 just for the sake of the video. Make it a little shorter here. So number 1, what do we get? Tails. Okay, second flip. Tails. So far my prediction was awful. Heads. And it's off screen, but it is heads. Okay, and one more flip. Tails. All right, so there's my experiment. My prediction was that it would always be heads. It was a terrible prediction. And I don't really have any reason, right? I didn't say why. I didn't say I think it'll always be heads because, and then some reason, right? And then I actually conducted my experiment, 5 flips. I got tails, tails, heads, heads, tails. Okay? So there you go. All right? Why was my prediction bad? Well, it didn't really make any sense. A better prediction would have been 3 and 2, right? Or if I'd kept it as 10 times, I could have said I think it's going to be even. Because the thing with the coin is that it's a fair flip, right? I mean, you got tails, you got heads. There's only 2 choices. It's never going to land sort of on its side. It's always going to land on one side or the other. You could get like really annoying and say, I actually scraped off the metal off the coin, and I discovered that the tail side actually has slightly more, which means it's a little heavier. So heads, okay, whatever. It's generally thought of as being a fair share. Okay, so there we go. Let's do a second experiment now. We're going to use this. So I got 3 of each color. I've got 3 black Lego pieces, 3 red, 3 blue, and they are all the same. Okay, that's important. If I was all of a sudden using different ones, like if I said, okay, I've got, I'm going to use Lego pieces that are 4 bricks long by 1 brick high, and I'm going to use 3 red, 3 black, and 3 blue. It's a fair experiment, right? If all of a sudden I swapped one of these reds out for that one, then all of a sudden the experiment's no longer fair, right? Because if I reach in and close my eyes, oh, I picked red. I wonder what I'll pick next time. Reach and close, oh, I picked red again, right? It's no longer a fair experiment. So for this to be a fair experiment, it needs to be a fair setup, right? Every piece needs to be the same size, just like with the dice, right? All the sides are the same. It wouldn't be a fair experiment if all of a sudden you had, 1, 2, 3, 4, 5, and then a second 5 on the dice. You didn't have the 6, right? It wouldn't be a fair experiment. Okay, same with if you decided to use a coin that had heads on both sides, right? So that's the idea behind a fair experiment. Okay, so I have 9 total pieces in here, 3 of each color. Okay, so my experiment is going to be called Draw the Lego Piece. And by draw, I mean pick out, not draw. Don't worry, you see my handwriting. We don't want me, yeah, you know. Okay, so draw the Lego piece. So my prediction is, this time I'll do a real prediction. So I predict that, how many draws should I do? Let's say 9. Hey, there's 9 pieces. So draw the Lego piece 9 times. And I predict that I will get even number of blue, red, black. Okay, so 9 draws. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and here we go. And I am going to close my eyes legit. And here we go. First draw, black. I'll do BL for that. Now, you kind of have to decide what you're going to do. Are you going to replace the piece each time, or are you going to not replace? I'm going to replace, and I'll tell you why. I'm replacing because I feel like it's like rolling the dice. When I roll a 2, I don't then take off the 2 and it's no longer an option, okay? But you need to kind of think about that before you do the experiment, before you do your prediction. Okay, eyes closed, second draw, red. Okay, throw it back in. Blue. Hey, so far it has been even, okay? I would keep going. I'm not going to do this for the whole video, but we got kind of lucky that it turned out even. Now, here's the thing. It may not, right? It's very, very likely even, it could be argued, that I would draw, 2 blues in a row at some point. Especially if I said I'm going to do this 1,000 times or 1,000,000 times, right? The chance that I draw blue a couple times in a row or red a couple times in a row, that's going to happen. It's almost certainly going to happen. I'm not going to always get, the same order over and over again, one each 3 tries, okay? Mathematically, yeah, sure, that makes sense. But in real life, that's not going to happen. Just like if you play, Monopoly with your family. Do you ever roll doubles? Yeah, sometimes you roll doubles, right? I might pick 2 blues in a row. You never really know, okay? And that's kind of the key point to the last thing that we're going to talk about, which is, how many times you do the experiment. How does that influence what happens in the experiment? So I'm going to flip my page over here. So let's say my new experiment is, let's go back to the coin. I'm going to flip the coin, and I'm predicting, since I've been learning here, predict even chance of heads or tails. That's my prediction. I'm going to flip the coin once. Here we go. Flip my coin. Heads. Flip 1, heads. So my conclusion after performing this experiment is that every time you flip a coin, you will get heads. What's my proof? Well, I did an experiment. Here's my proof. I did an experiment, I flipped the coin, and every time I flipped it, I got heads. I flipped it, and it was heads. Every time in my experiment. Okay? So my proof, therefore, is that when you flip a coin, it will be heads. Fair experiment or not fair experiment? Okay, obviously, that's not fair, right? That doesn't make any sense. First of all, the coin has 2 options, so there's no possible way I could do an experiment without at least doing it twice. And if I did it twice, could I get heads? Let's just pretend. Oh, I flipped it. Oh, heads again. Oh, therefore, shut it down. The evidence is complete. Every time you flip a coin, it's no, okay? You have to do the experiment more times than just a couple, right? What do you think would happen if, let's say, we got the whole class together? Let's pretend that there's 25 kids in our class, okay? And we each do the experiment where we flip a coin, and we only flip it once. Okay, what do you think would happen in the class? Is it possible that all 25 kids would flip heads on their experiment? It's possible. Okay, it's not impossible using our probability talk. It is possible, but it is very unlikely. okay? If I flip a coin once, my chance of getting heads is equally likely because there's only two choices. It's heads or tails. So if I flip a coin once and I'm trying to get heads, I got an okay chance, an equal chance of getting that heads. But the more times I add to this experiment, the less likely I'm going to get what I want. So if I said I want to have heads every time, that's what I'm trying to prove because like I'm some weirdo or whatever, and I have 25 kids flip it, the chance of all of us getting heads is very unlikely, right? We would expect to see, 13 kids get something and 12 kids get the other. It might not work out that way, right? We might get, 15 versus 10 or something like that. But we're probably not. Very unlikely that we're going to get 25 one way and 0 the other way. Could happen, right? Could happen, but it's very unlikely. We're more likely to see something that is closer, okay? So that's sort of the second point of these experiments, is that the more times you repeat the experiment, the more likely you will see what you expect, okay? So I expect if I flip a coin, I will see heads or tails, and if I flip it 1,000,000 times, I would expect to see about half the time, so 500,000 times heads and 500,000 times tail. That's what I would expect to see. Now, it might not be perfect, but the more times you do the experiment, the more times you will, or the more likely you are to get to this sort of mathematical idea, right? If I roll dice 6 times, I might not get a 1 once, a 2 once, a 3, right? I might get 1, 2, 3, 4, 5, 6. I might get 2 2s and no 5s, or who knows, right? I might even roll 6, 6, 6, 6, 6, 6, 6 times, right? But probably not. I'm probably going to get a mix, right? And if I did the experiment 6,000,000 times, I would expect to see somewhere around 1,000,000 times for each number. Maybe not perfect, but pretty close. If I did it 6,000,000 times, I definitely would not expect to see 3 come up 4,000,000 times. I mean, that is, the math behind that, it makes it almost impossible. Not quite, but almost impossible. All right? So that's sort of the two things I wanted to bring about today. The idea that, one, that you can create an experiment, a probability experiment, where you use dice or coins or whatever you have around the house to think of the experiment and then predict what you think will happen, okay? And we call that sort of like a theoretical probability. So it's the idea of what we think should happen. And we can use math to come up with that, and you will do that in later grades. Then you conduct the experiment, okay? And just to keep it interesting, just do the experiment once, or just do it twice. Try to just do it a few times, and then bump up those numbers, okay? So like if you're flipping a coin, try just flipping a coin twice and seeing what happens. Maybe you get heads, maybe you get tails, maybe you get a mix. But then try it 20 times and keep track, and see if you get closer to your prediction, okay? So there you go. There's a little bit on probability. Probability, by the way, is one of those things I feel like if you speak to adults, unless they're sort of like math teachers or somebody who's really into math, they don't really understand probability. And I have proof of this, by the way, that people don't understand probability. My proof is people play the lottery. People go to casinos, okay? These things make a lot of money. And the reason why these things make a lot of money is because the people who run those things do understand the math, okay? And they make games or lotteries that make them money. They don't make a game where the probability is in your favor, because then they wouldn't make money, okay? They make games where the probability is that they will make money. Could they make some, casino game where people are pulling those handles and everybody wins? It could happen, but the probability is very low. Okay, they make games where the probability of them winning is very high, and that's why they make so much money. Okay, so there's sort of my own little theory and my evidence for it. Okay, so understanding probability is very useful as a human, but it's also great because then you start to play games, like when you're playing Monopoly or Catan, when you play these games, or poker even, right? When you're playing these games, even not for money, just for fun, but when you play these games for fun, you can sort of use the probability in your favor. For example, when you roll 2 dice, if I get 2 dice together and I roll them, and you ask kids what could come up when you roll 2 dice, well, you might get, kids will sometimes say, well, you get a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12, which is actually wrong, because there is no way to get a 1, right? You can get a 2, that's the lowest number you can get. So kids will be kind of confused about that. And I'm not going to sort of spoil it for you, but try getting 2 dice and rolling them. And even don't make a prediction, but just keep track of what happens when you roll 2 dice and see what numbers come up the most, because there's actually some math behind that. And if you understand that math, then you can use the numbers that come up the most often to your advantage in some games. All right? So there you go. Take it easy.